Yeah, good morning friends. Myself I am Dr. Satish Reddy, Biomedical Engineering Department, Excel Engineering College. So today we are going to talk about the basic biosignals and biomedical difference between the biomedical signal and biosignals, and what are the few elementary signals what we are going to use and its significance in the real-time applications. So coming to the point, the first one is that biosignal, and few people are going to say that the biosignal and biomedical signal are both are same. Okay, more or less both are same only 90%, but except the small definition. So the biosignal you are going to define as there is a signal produced by any living organism that we are going to treat it as a biosignal. That means you can take from any animals or human beings, whatever it is, any living organism, it is treated as a biosignal. And biomedical signal, this is the signal. It is a purely physiological signal gathered by a trained technician, which is used for the clinical applications and the treatment. So first we are going to speak about the significance of signals and systems, especially for the bioengineers, and its applications. We are going to found it in biosignal processing. So today we are going to speak about only the elementary signals and how we are going to represent and what is the purpose of that. So coming to the picture here, I mentioned only the 4 signals and we look into deep, including the classification. See here the unit step signal. Mathematically it is represented with as E of t. So why you are looking into U of t? There are 2 ways to represent the signal. The first signal is that we are going to say that is a continuous signal. So that's what I represented as a U of t. The same signal we can represent it is in a discrete mode. You can say it is a discrete mode, and we are going to say that is a U of n. The discrete mode signal representative we see in the next class. In today's class, you are going to speak about only the continuous time signals U of t and how you are going to represent it. You see from the graph, you can observe that the existence of the signal here, the signal from 0 where you are going to get the amplitude is of 1, and up to t it is extended, and we didn't found any kind of a signal for the value of t which is less than to 0. That's what U of t is always 1 when t is greater than 0, and it is equal to 0 for t is less than 0, you can say, or it is otherwise. So that is a well defined. And what is the significance of this unit step signal? The significance of the unit step signal for you can use it as a basic test signal for any kind of the system, or we can say that you can separate any kind of the complex signal in terms of the elementary signals. Out of that, this signal is has plays a significant role. And the next signal, it is what we call as a unit impulse signal. That is represented with del of t, and the del of t is equal to 1. You can observe from the graph itself. There are 2 things here there. You can remember easily, either graphically or either mathematical orientedly. So it is easy to remember as graphically. So from the graph itself, we can build the mathematical equation. So it is from 0. So where we are going to get the signal when at the t equal to 0, it is denominated as 1. So del of t is equal to 1 and t equal to 0, and then it is 0 for otherwise signal. And this is also the same application. This is as a basic test signal, and using the mathematical equations or any mathematical formulas, we can build a unit impulse train also. And the next signal, we are going to say that the UR of t, that is what we call a unit ramp signal. When t equal to 2, it is the output is also t when t is greater than 0, and it is 0 for t less than 0. And this is a very well known signal. So that is what we call as a sinusoidal signal, and mathematically represented with x of t is equal to sin omega t, and where it is separated into the fundamental components like frequency, and then amplitude, and then phase. So here these 2 by represent its an angular frequency, and here in the figure I draw the sin of t along with the cos of t, You see the basic difference, only the difference between the sin of t and the cos of t is that it is 90 degrees out of phase. We can say that the cos 2 pi ft, where it is having only 90 degrees phase difference. Okay. Yeah, in previous class we studied the few 4 basic fundamental signals. In this class we are going to see the signals basic operations. That means that what kind of operations we are going to do on the signals. Before going to do the operations, first you know the significance. What is the purpose of we are doing this? For example, in order to analyze the complex signals, we need to represent the complex signals in terms of the basic fundamental signals. Maybe sometimes you are going to add 2 fundamental signals, or maybe going to subtract, or maybe going to multiplication, or sometimes it may be the time shifting. That means we are going to shift the signal with respect to the time, and in that case we are not going to change any kind of amplitude. And sometimes you are keeping the time as a constant, and we are going to make playing with the scale the amplitude. So these are the few fundamental signal operations we are going to perform on any kind of the signal. Basically, for practice purpose, we are going to do on the elementary signals. The first one is the time scaling. This is the time scaling version. For example, we are going to say here the time scaling version. For example, I am giving you x of t. For example, this is the t. Maybe this is the continuous time signal as I am drawing, and this is the x of t, and you can say that this is the plus 1 and this is minus 1. Now I want to make it x of 2t, means here we can compare with the normal notation x of a t. Here it is called as a scaling factor. That means mod of a should be greater than, if it is greater than 1, then we are going to get, it is a compressed version of the signal. And mod of a is less than 1, then you are going to say it is an expanded version of the signal. Version of the signal. Now we can select the x of 2t, then we are going to say it is greater than 1, it is a compressed version of the signal. So finally we are going to draw the rough pictorial representation x of 2t, where my time has been reduced by 2 times. And similarly, this version is going to say that this is the compressed version, and we are going to say x of t by 2. Now is draw this and the expanded version, and this is plus 2, so minus 2, and this is plus 2. So compared to this you are going to say that expanded version. So this is what about all the time scaling, and then the time shifting operations. We are going to say that x of t plus or minus t naught. We are going to say the plus t naught. If it is a plus t naught, we are going to say it is the negative shift, and it is a minus t naught, we are going to say it is a positive shift. Means if it is a plus t naught, we are going to shift the entire signal into the negative values, and if it is a minus t naught, we are going to shift the signal into plus values. So for example, we are going to see the x1 of t. x1 of t, for this I want to draw x1 of t plus 1, and the next x1 of t minus 1. So for x1 of t plus 1, x1 of t plus 1, you can assume it, just I want to shift one term towards the negative. Means here the signal has been started from 3 and it has to started from 2, and the signal bit should not be changed, and it has shifted back one position, so it is ended with minus 4. So in this case, two important points you have to keep in your mind while doing this operation. The first point is that the width of the signal remains constant, and the amplitude of the signal is also remains constant. The time shifting operation, only the signal has been shifted by t naught times, either towards the positive or towards the negative, depending the value of the t naught. And the third operation, you are going to see the time reversal operation. It is easy to remember. A time reversal, it is what we call as this we are going to say as mirror image of the signal. Means that you draw the signal and you put the mirror in front of the signal, what kind of signal image you are going to see, and it is always represented with x of minus t. For example, you can say that the unit step signal u of t, this is the well-known elementary signal, and for that I want to draw u of minus t. So this is my u of minus t. This is the t, this is the 1, and this is the t, and this is my u of minus t. Okay, remaining operation we will see in the next class.